Hello participants and welcome to this e-learning course on chromatography jointly organized by Sheth M and Science College Patan and DIPAM Foundation. Friends, today we are going to discuss a very important advanced and useful analytical separation technique which is called supercritical fluid chromatography. Friends, why the revival of interest has nowadays changed towards supercritical fluid chromatography? It is because of its two very important aspects. One is high efficiency and second one is the speed of analysis. Also, beneficial features of both GC and HPLC are found to be present in supercritical fluid chromatography, and which makes it a unique propertized technique among the available separation techniques. But what are those beneficial features? We will just go through each of the features along this talk whenever they intercept us. Moving ahead, the historical development in supercritical fluid chromatography. As we all know, chromatography and gas chromatography were all around 1950 or before that. But somewhat around in 1962, for the very first time, the supercritical fluid chromatography was used by Clasper and Turner, and after 20 years, that is somewhat around 1982, the first commercial instrument came into market. That first commercial instrument was from the Hewlett Packard, after which the capillary column was introduced in this supercritical fluid chromatography by a very popular platform, Lee Scientific. Still, when the development was going on, somewhat around in 1992, again Hewlett Packard came up with a second advanced supercritical fluid chromatograph. And then after, it went on increasing and increasing, and today we know that there are groundbreaking inventions going on and on in supercritical fluid chromatography. The three major aspects on which supercritical fluid chromatography works includes the stationary phase, the mobile phase, temperature and pressure combinations. Friends, a very long journey has helped us today to gain a very important instrument in separation science, and that is supercritical fluid chromatography instrument. Understanding supercritical fluid through a phase diagram is very much important. Different conditions of pressure and temperature are maintained in a system. You can see over here, pressure is on the y-axis and the temperature is on the x-axis. And we all know that two states coexist along the two sides of the line. If particularly we take this line, you can see in this much part, it's a gas liquid equilibrium. Over here and here it's a gas solid equilibrium, and over here and here it is a solid liquid equilibrium. So two states coexist along the two sides of the line, and with the increase in temperature the phase transition occurs from solid to liquid and liquid to gas. Remember here very well that if I go on increasing the temperature and also keep on maintaining the pressure, I can shift the state or the physical state of a sample from solid to liquid and from liquid to gas. And there is a triple point present where all the three states can coexist together. So these are some of the important aspects of the phase diagram. But understanding the supercritical fluid via phase diagram is somewhat very important. Each substance has its characteristic critical point. Substances, when subjected to a temperature and pressure above this critical point, attain supercritical state. If you look into this figure, this particular point is a supercritical point or a critical point above which, if I rise the temperature, above which, if I rise the pressure, I am going to get that particular chemical compound in its supercritical state, where there is no line of differentiation between the state of liquid and the state of gas. So if I just compare it on the x-axis, we are somewhat around 300 Kelvin, and if I go on the y-axis, we are somewhat near to 100 bar pressure, but lower than 100 bar pressure. So if I cross this, if I increase the pressure, if I increase the temperature, I will reach in this area, which is fundamentally called supercritical fluid zone. And in the supercritical fluid zone, the state of my sample will neither be liquid nor be gas. It will be somewhat which cannot be differentiated very easily, and that is called supercritical fluid state. So please remember this point, that as and when you cross this critical point, you reach to the zone where your molecule or your chemical is in a supercritical state. Understanding the supercritical fluid, there are two ways to attain supercritical state. Number one, by increasing the pressure about critical pressure. So this critical point going above in this part is going above the critical pressure, and hence you say that you are in a supercritical state. And second, by increasing the temperature above the supercritical temperature at a constant pressure, you can say that you are going towards the attainment of supercritical fluid. But let us just go a little bit more basic for a while and define critical pressure as well as critical temperature. Critical temperature is the temperature above which gas cannot be liquefied regardless of the pressure applied. So if once I cross this point and go away, you can never transform this state into a liquid state. Similarly, critical pressure is defined as the pressure required for liquefying a gas at its critical temperature. Each substance has its critical characteristic critical point. So friends, these four typical slides are just for making you understand that how we are going to reach towards a supercritical sample, because this particular chromatography, that is supercritical fluid chromatography, has very much a resemblance with both HPLC and gas chromatography. The major two or three factors in which they differ includes the first, mobile phase, because in GC you have gas as a mobile phase, in HPLC you have a liquid as a mobile phase, over here you will have a supercritical fluid as a mobile phase. Number two, we have never seen or we have never used any kind of moderators or any other compounds along with the mobile phase, either in GC or in HPLC. We are going to use them over here. And here, as we are going to use a supercritical fluid, we need to maintain the temperature. That is also very important, which is not always maintained in HPLC but maintained in GC. So this is how you can differentiate between a supercritical fluid chromatograph with the gas chromatograph and the high pressure or performance liquid chromatograph. Understanding the supercritical fluid through the critical temperature and critical pressure was the last thing that we did. Now let us understand how we can achieve a supercritical fluid, that is a state where you can say that there is no line of difference between a liquid and a gas. Friend, in this animated video, it's a real experiment rather to say an animated video. This particular zone where you can see a line of separation is liquid and above all is a gas. And now see, when this particular person will make changes in the pressure and temperature, he will be able to reach the supercritical fluid state. Let us first see this whole video.
See on screen here is we have a cell, and this is a sealed cell, and there's a camera point.
First of all, he is speaking, it's a sealed cell. When the sealed cell is used, means you have packed it so tightly that its pressure becomes constant as of now. So with the increase in temperature, there will be something that is happening. So as of now, when he is sealing the vessel, the pressure has initially been made constant and he is going to vary the temperature. See what happens.
Pointing to the front of the window. So if I shake the table, we can see the liquid inside vibrating. So we have a liquid and we have a gas on top, and what we're going to do is we're going to heat it up. So if we flick the switch,
we are going to heat it up. Temperature is changing. It's a sealed vessel, so initially the pressure was constant.
On the front of the demonstration, We're going to heat the cell up, and because it's a closed system, what we'll see on screen is
it's a closed system. Few thermodynamics aspect. You can still see the liquid and the gases there above, but see what happens when the temperature is increased.
you'll see the liquid start to boil. And as the temperature increases, the gas moves from the liquid to the vapor phase, and the density of the vapor.
See, the line which was visible earlier when the video started, which was easily separating the gas from the liquid, is now getting blurred. And see what happens.
Phase increases and the liquid phase decreases until we reach a certain point when the two become indistinguishable from one another, and this is a supercritical fluid.
When the two becomes indistinguishable from one another, it's a supercritical fluid. You can see the two have now started becoming indistinguishable. आप इन दोनों को अपनी आंखों से जुदा नहीं देख पा रहे हैं. So you have reached the state of supercritical fluid, or you are on the verge of reaching that state.
So you'll have noticed that the dividing line between the liquid phase and the gas phase has now almost disappeared, and we've got a homogeneous mixture. So that's now our supercritical fluid. And then if we run the demonstration in reverse, so now we'll cool the cell down and we'll see the opposite thing.
Now he will cool the cell down. We already know going above that critical temperature is always a supercritical fluid state. When you will come down suddenly from there, the reaction will be reversible and you will get back the liquid which was present.
Happen. So when the temperature of the cell reaches approximately 45 degrees, we'll see this phase separation occurring, and we'll regenerate the liquid phase and the vapor phase. There we go. So you can see we get this fantastic snowstorm effect where the gas comes out of the solution.
Nothing but the gas is getting condensing back to the liquid, and you will soon see again the layer that is separating, the line that is separating the liquid from the gas.
And rises to the top, and we get droplets of the liquid forming, and these fall to the bottom. And if we shake the demonstration, you can see now we've reformed the meniscus, so the separation between the liquid and gas phases.
So friends, this was all about understanding the state supercritical fluid. Now, the reason behind taking 4 or 5 different slides and explaining you supercritical fluid was because the theme of this technique is supercritical fluid. I hope you have understand what I was telling. So now we are moving further with the properties of supercritical fluids. The changes in pressure and temperature can bring about higher change in the density, viscosity, and diffusivity of the supercritical fluid, leading to its higher use as an eluent. Just by making a change in the temperature or pressure, you can change its fluidity, you can change its viscosity, you can change its density, and hence they can act very well to elute other components. And as we know in chromatography, elution is a very important step. Now if you remember the initial slide where we have told you that it's a blend, it's a mixture of the benefits of both GC and HPLC. And the first reason comes over here. It behaves like a liquid, that liquid which behaves as a mobile phase in a HPLC by the power of solvation. In HPLC, the liquid mobile phase has the capacity to dissolve the analyte. Similarly, in the supercritical fluid chromatography, the mobile phase supercritical fluid has the power to dissolve the sample. So it's like HPLC. Like the gas, means in GC, mobile phase is your gas and it has a property of effusing through the solid pores of the stationary phase. So the supercritical fluid also has the property of going through the pores of the solid stationary phase. So this is the first reason that it has a blending, it has a mixture, it has the benefit of both GC as well as HPLC, and hence it is more preferable. Over here you can see it has both liquid, it has gas, and it's a combination of two that has led us to the supercritical fluid. Its principle is very much similar to what we have learned earlier. Supercritical fluid chromatography, as any other chromatographic technique, is based on the partitioning of the analytes between the stationary and the mobile phase. The mobile phase is a supercritical fluid or a supercritical state in SFC. The column stationary phase is similar to that either used in HPLC or used in GC. So you can imagine you have a very wide choice of columns. You can use the columns from HPLC, you can use the columns for GC, but only thing that is to be taken care of over here is that your mobile phase has to be a supercritical fluid. Then and then only the phenomena or the principle of supercritical fluid chromatography will help you to go towards your results. Instrumentation of supercritical fluid chromatography. The earliest system that was developed way back in 80s was somewhat similar to GC. It had open tubular chromatography columns with polysiloxane columns and pressure compatible UV detectors initially in 80s, after which pure carbon dioxide as a mobile phase was used. There were capillary columns, oven, pump for pressure, and detector. But using modifiers with the mobile phase was the first change that came, which helped to overcome the issue of regulated flow, velocity, pressure, long retention time, and low efficiency. Why were these problems coming before adding modifiers? If you look carefully to this first section, pure carbon dioxide was used as a mobile phase. And you know very well that when we coin the word pure carbon dioxide, it is non-polar in nature. So, being non-polar in nature, because of the opposite dipole moment, there were some problem in the retention time. And to overcome that, scientists came with a solution that keep carbon dioxide as a mobile phase no problem, but you add some modifiers that can change the polarity of the mobile phase and help the substance to come out early. So the retention time, which was taking too long, will now be shortened. But after adding modifiers, there were some other issues, like issues involving the incompatibility with the detectors. When you were trying to fit this instrument in the detectors, it was not responding. So, using the pack columns as in liquid chromatogram, these types of columns that are used in advanced HPLC instruments were used. And even after that, several modifications were obtained, adopted, and today you will be surprised to know that supercritical fluid chromatography has a compatibility with nearly 12 detectors. It has more than 12 detectors compatibility, but nearly 12, which even HPLC is not having. So in the case of detectors, supercritical fluid chromatography is even more prominent than HPLC in some aspects. This is a simple flow chart of supercritical fluid instrumentation. This is a CO2 cylinder, which is our mobile phase. These are modifiers, reservoirs. I will explain to you. Just keep one thing in mind from this flow chart, that there are two separate pumps. One pump is for CO2, second pump is for modifier. Now you will have a question, why so? No doubt you know, because the pressure drops. What I taught you in HPLC, low gradient and high gradient. But apart from that, there is another important point over here, because the state of CO2 and the state of modifiers will not be completely same. Henceforth, you need separate pumps to suck them. And mind well, I will come to the state of CO2 when it is filled and kept in a cylinder and when it is used by us are both different states. It might be stored as a liquefied gas and might be used as a supercritical fluid. So once in this mixing chamber, you have both these modifiers and mobile phase. It has been shifted to auto samplers, from auto samplers to injectors, from injectors to column oven, and from column oven to detector. But before they go to detector, or once they pass through the detector, they are even sent to back pressure regulators. In this particular instrumentation, we are mainly going to focus on those aspects which we have never discussed in GC or HPLC, and back pressure regulator is one among them. Friends, anyone or everyone when tries to explain any scientific concepts through charts or pictures, as we all know, it is little difficult to understand. But here I have a very good instrumentation video where each and every part, it's a function, it's a mechanism, has been explained in short. So first of all, we will go through that, and afterwards we'll see each component associated with supercritical fluid chromatography instrumentation. This video is from Waters Company, so we highly appreciate and thankful to Waters Company for giving such videos on Google from where we can get it. Waters is a very prominent company in liquid chromatogram techniques, and we are thankful to Waters that they have given us such a supportive video that we could share with all of you. Now, we will just go through this video and see what are the flowchart parameters from where the mechanism and the instrumentation is working.
Supercritical fluid chromatography is simply chromatography where the mobile phase is a supercritical fluid. In this
The mobile phase is the supercritical fluid.
case, carbon dioxide. Supercritical fluid chromatography is very similar to liquid chromatography. The instrumentation is nearly identical for both forms of chromatography.
The instrumentation is nearly identical for both the forms of chromatography. Let it be liquid chromatography, that is HPLC, or let it be SFC, that is supercritical fluid chromatography.
This is the method station 2. It's an analytical supercritical fluid chromatograph as opposed to other chromatographs that Thar makes, which are primarily preparative. This instrument consists of a pumping system.
This is the pumping system. You can see two separate pumps. Remember the chart that I showed you just now. One pump will be for CO2 and the second pump will be for the modifiers. And I'm going to teach you, or rather discuss with you, what are modifiers.
Which delivers high pressure carbon dioxide to the chromatograph. A second pump is used to deliver a co-solvent or modifiers. At the top of the pump we see 6 reservoirs. These reservoirs contain a co-solvent or a modifier.
Reservoirs are nothing but glass vessels which can be filled with liquid modifiers, and we know why we are using glass, to keep them anti-corrosive and to maintain the purity of these modifier solvents.
The co-solvent and CO2 are delivered to.
You can see this flow chart. This tar, a company, it's a CO2 cylinder. On the second side you have the modifier. Both through the pumps are brought to a static mixture from where they will be mixed properly and sent towards the injector, then to the column, and then towards the detector.
A static mixer. The static mixer's function is to homogenize the CO2 and the co-solvent.
See, here a homogeneous mixture of CO2, that is our mobile phase, and our modifier will occur, and then this will be moved forward.
The homogenized mobile phase is delivered to this auto sampler. It's equipped with 2 48 station sample holders.
These are sample holders in which vial filled with your sample will be placed, and this is the auto sampler part from where the sample will be taken and will be loaded in the needle and will be thrown towards the injector.
For a total of 96. It's also equipped with an injection valve. It picks up the sample, and the sample and mobile phase are delivered to the front of the chromatographic column. This is the column oven.
See, this is the column oven. As we all know, now onwards we need to maintain the supercritical fluid state of our mobile phase, and therefore we need an oven to maintain the temperature and pressure. Along with these rod-like strips that you are getting visualized over here is nothing but the columns, and there are different machines having capability of different quantities of column that can be placed at a time, although you can use one at a time.
We can have up to 10 chromatographic columns in the oven. Once the sample elutes from the end of the column, it's delivered to the detector. In this case, it's a Waters photodiode array detector, the 2998 model. It leaves.
There are more than 12 detectors, minimum 12, that can be compatible with this system. Over here we have just seen the photodiode array detector.
The detector and is delivered to the back pressure regulator. Up to this point, the instrumentation is identical to the liquid chromatograph. The unique part of an SFC is the back pressure regulator. This
is the first instrument, back pressure regulator, which is newly added when you compare this instrumentation system with either liquid chromatogram or gas chromatogram. And even in few gas chromatogram, today people are seeing the back pressure regulator, but in liquid chromatogram, we have not seen back pressure regulators, which is present over here.
Controls the pressure throughout the system, and the pressure also controls the flow rate through the column. The system uses two forms of software.
If you look very carefully here, you can see co-solvent stands for modifiers. The cylindrical vessel is nothing but the carbon dioxide containing vessel. They are mixed in this static mixture, passing through these high pressure pumps. When they will move forward and when they will reach this point, these are 10 different separating columns, from which this first column, which is marked in green, is working at present and where the separation will take place.
One we call superchrome. This is used to.
You can see once it passes through this column, it is going towards the detector, and from the detector it will move away, but there is an automated back pressure system which is there to maintain the pressure in the system so that the supercritical fluid state of the mobile phase is maintained. There might be a question in your mind that why you are using this back pressure system. Back pressure system is used to maintain the pressure, because we know that the combination of temperature and pressure jointly can make any molecule, any chemical into its supercritical fluid state, and to maintain that, back pressure is must.
Operate the chromatograph, and a second software system called ChromeScope is used for the chromatographic data handling. We're using the Empower software to control.
You can see that on the top end we had a detector. Over here also we are having another detector which we will just now listen to.
The chromatograph and to do the chromatographic data handling. The Resolution 2 is simply a method station 2 with a Waters 3100 mass spectrometer added to it.
So you can even have
when this
mass
is done,
spectrometer added
the
to
system
it.
is called the Resolution 2, and instead of being controlled by Empower.
So friends, this was the whole basic system of a supercritical fluid chromatograph. Now, moving forward with the explanation of each component, the very first component that we have is supercritical fluid instrumentation detail components. Number one, the solvent delivery system. Number two is the injector. Number three is the thermostated column. Number four is the restrictor or the back pressure device. Number five is the detector. Number six is the data handling system. Friends, purposefully I have not mentioned here mobile phase because it's a gas, as we all know. Apart from this, you can just go through the detail that is given on the right side. It's a step-by-step process, and we must read it once because just now we have seen the video. Let us assume the mobile phase to be the supercritical fluid carbon dioxide. Carbon dioxide or other mobile phase is stored in the pressurized cylinder and modifier in a reservoir. Two different pumps are used to pump the CO2 and modifier in a requisite amount to a mixture. Where mixing is appropriate, desired ratio is carried out. The sample is introduced into the injector. It is carried by the mobile phase flowing through it to the supercritical fluid column. The eluent from the column goes to the detector. The eluent may be discarded or may be collected using the fraction distillator or fraction collector if you wish to. It is not mandatory. This is a simple process. but we are going to focus on each component highly detailed so that we can understand the theme behind it. Mobile phase. Highly pure solvents are required for chromatographic technique, and these are the major components of overall process expenditures. The CO2 used as a supercritical fluid mobile phase is highly pure and is available in high pressure steel cylinders. This cylinder can last for huge number of analysis runs. So first of all, as of now, for this discussion, we will be sticking to carbon dioxide as a mobile phase. Friends, mobile phase in supercritical fluid chromatography, apart from carbon dioxide, can be nitrous oxide, ammonia, N-butane, diethyl ether, tetrahydrofuran, and ethane. But there should be some properties in them to serve as a mobile phase. This property includes inertness, they should not react much apart from being a carrier. They should be compatible with the detectors, and critical parameters should be achieved. Now, what do we mean by critical parameters? Pressure and temperature. If your mobile phase is not responding properly to the pressure applied and the temperature gained or lost, and it's not getting converted into supercritical fluid state, then it is not a good mobile phase for our technique. But all these chemicals, molecules, chemical entities are very much critical and sensitive towards the temperature and pressure, and hence are very easily accessible as supercritical fluid mobile phases in supercritical fluid chromatography. Selection of CO2 as a mobile phase. Why? See, it has critical pressure around 31.1 bar. No doubt, when we compare it with our atmospheric pressure, it is very high. But for an instrument having a pump, whether it's an HPLC or whether it is a supercritical fluid chromatography, 31 bar is not a big job. We are going up to 200, 300 bars. So it's achievable. And it's a temperature 72 degrees Celsius, again achievable. Sometimes, apart from using carbon dioxide, we have seen people using xenon as a mobile phase, but subject to condition they are using IR detectors as xenon is not absorbed much in IR spectrum. So the new thing for us that apart from CO2 and all those mobile phases that we saw just now, xenon is also among them. Another important point that you have these many mobile phases, then why to focus on CO2? Other solvents have safety issues and incompatibility issues with the detectors. If you use some particular mobile phases, they do not sense or they do not show a proper signal to the detector. Even apart from all this, why is CO2 in a win-win situation in a mobile phase? Because it is easily achievable, pressure and temperature are comparatively low, density is achieved easily at a moderate pressure and temperature. It is non-toxic, it is non-corrosive, and excellent for non-polar samples. These are some of the pros why CO2 can be used as a mobile phase. And even scientists nowadays are calling it as an eco-friendly mobile phase. So friends, these are the basis on which CO2 is selected as a mobile phase. Why modifiers are essential? If you go back to the chart, you will see that I have added modifiers. Modifiers are essential in mobile phase. Although being one of the most prominent mobile phase, there are several issues using CO2 as a mobile phase. It's a very high retention time, non-elution of analytes, and separation of highly polar analytes is impossible for a non-polar mobile phase like CO2. If you recall and if you look over in the slide, CO2 is a non-polar mobile phase. But the mixture that is going to be separated have all the analytes of highly polar quality. Then CO2 will not be able to drag them, even it acts as a carrier because their nature are opposite. And in such situation, you need some extra chemical, extra material that can help CO2 reduce its non-polarity, get a little bit of a polar property and help to separate the compounds so there will be no issue of non-elution of analytes. Otherwise, sometimes sample does not come out, it remains inside. Over here, using modifier can help you overcome that issue of a non-polar mobile phase like CO2. Modifiers and their functions. Generally, they are organic, solubility of polar analytes, reduce the interaction between sample and stationary phase. See, when CO2 mobile phase is mixed with a modifier, it will change its nature from non-polar towards polar. And when it will change its nature from non-polar towards polar, it will now be able to make polar analytes soluble in itself. And when a mobile phase is able to make soluble polar analytes in itself, it will help them drag away from the stationary phase and hence reduce the interaction between the sample and the stationary phase to facilitate the reduction in detention time. If you will go quickly away from the stationary phase, your retention time will decrease. Easily available, cost effective, and low toxic. These properties are present in one organic solvent, or rather to say solvent, and that is methanol. Hence, methanol is an appropriate chemical to be used as a modifier in supercritical fluid chromatography. Solvent delivery system. This particular solvent delivery system is responsible for the transport of solvent through injector and to column, also conducting a controlled flow of mobile phase rate and the pressure of the system. When this much importance is given to a solvent delivery system, it should have a supercritical mobile phase pump, liquid modifier pump, and a back pressure regulator. So these three combine and form a solvent delivery system. Pumps in supercritical fluid chromatography. The pressure of the mobile phase is the most important as it controls the density of the mobile phase and the solubility of the solutes. Pump must be capable of a pulse-free flow or pulseless flow as it requires to vary the proportion of mobile phase composition for better elution. There are fundamentally two types of pumps. One is the syringe pump and second one are the reciprocating pumps. Generally, it is observed that when you are using open tubular type columns, you generally go with syringe pumps. But when you shift to these packed columns, porous columns, then you go with the reciprocating pumps. And mind well, as you are going to work with high pressure and even temperature, the pump and the seals to avoid leaking are made up of such a good quality that they can tolerate the high pressure that is going to be bombarded on it. Maintaining the physical state. Supercritical fluid chromatography, according to me, this is the most important phase or aspect. You are willing to conduct this experiment by keeping your mobile phase in a supercritical fluid state. And you should have some instrument that can maintain it in that state. CO2 or the SFC mobile phase is supplied from gas cylinder containing liquefied gas in equilibrium with its gaseous phase. Modifier is liquid at room temperature and pressure. So fundamentally, you have gas in a liquefied state, you have modifier in a liquid state, and henceforth two separate pumps for the delivery of CO2 and for the modifier are required. CO2 and the pump head are pre-cooled to about 4 to 5 degrees centigrade in order to prevent evaporation. If the pump head gets heated, sometimes your carbon dioxide will get evaporated. You are not willing to evaporate, you are thinking to keep it somewhere between liquid and gas, not above gas. Keep this thing in mind, and therefore pre-cooled head pumps are used. And for pre-cooling, generally we know coolers or chillers are adjusted and they are filled with ethylene glycol. Friends, if you don't know, remember very well, for any practical purpose, when you want to bring down the temperature, generally instrument called chillers are used, chillers are used, and they have ethylene glycol which is kept rotating over and over to the surface which you want to maintain at a low temperature. This is important. If you will go too high temperature, they can evaporate. We are not interested in evaporating. We are interested in keeping it between liquid and the gaseous. state. Keep this thing in mind. Injectors are fundamentally of two types. Loop injectors. I will not be discussing anything on loop injectors because you already have learnt in HPLC those loops. They are called loop injectors. The load position, the inject position, everything. But now I am going to focus on inline projectors. See, the eluent, that is the mobile phase plus your modifier, is passing from this reservoir and the mixture and is directly going into the column and so on. But when you want to inject a sample during this continuation phenomena, you will directly inject the sample which will directly go into the column. So such type of injectors are called inline injectors and they are more versatile nowadays. People are using them drastically because flexibility in the volume of injection. As you remember, the loop in the HPLC was somewhat around 20 microliter or 30 microliter. But over here, there is a flexibility in the volume of injection as well as non-diluted sample can be injected. You need not to dilute the sample before injecting it. You can directly inject the sample. These are the two mega benefits of using inline injectors over here. A high pressure pump directly helps the sample to enter into the flow of eluent, that is through the feed, directly enters into the flow of eluent. These are some of the major aspects which make inline injectors more useful, more prominent, and more likable compared to loop injectors in supercritical fluid chromatography. Guard column. There is a guard column which is placed before the main column to avoid clotting, to avoid impurities getting inside. For preventing the clotting of the columns and establish on-filter facility, activated carbon or alumina based adsorption filters are used, and these filters are nothing but guard columns. This helps in increasing the lifespan of the column. If no dust particles or other impurity particles will go inside the column, clogging issues will not be there. And if clogging issues are not there, you can use the column for more and more years to come. And henceforth, we have written that the lifespan of the column will increase. Oven and column. The same oven system used in GC and sometimes in HPLC system can be employed here. Two major types of column utilized here are packed column and capillary column. And we are knowing the huge detail of packed column and capillary column through the GC techniques that we have learned. Columns. Packed columns. Stationary phase are filled using an adherent and packed in a stainless steel. Modified silica being inert, flexible and strong makes the packed column more prominent in supercritical fluid chromatography. Whereas capillary column made up of a specialized purified silica with a polymeric stationary phase and is coated on the wall. So I am just reading it because I have already explained you these things in detail. In a capillary column, you are just coating on this surface, whereas in the packed column, you are filling it totally with the powder. So in the packed column, there are tiny pores through which you have to pass, whereas in capillary column, there is a small pathway in the between where nothing is there because the stationary phase is just stuck on the walls or the inner walls of the column. The size of the column used here is less than the column used in the GC in terms of internal diameter. So friends, according to what I know, people today in supercritical fluid chromatography are very much adjustive to the packed columns also. They do not form any difficulty or they do not found any difficulty when practicing the experiments using packed columns. Back pressure regulators. BPR are installed behind the detector to maintain the pressure throughout. Why? Because the microprocessor unit collects the data of pressure, oven temperature and detector performance to control the related pieces of the instrument. If the back pressure is not controlled and the pressure falls, and even due to the fall of pressure, there is a variation in temperature, and even if not, mind well, with these small or big changes, the supercritical fluid state of the mobile phase may be affected. And if that is affected, then there is no need of this instrument, no need of the mobile phase, as it is not able to stand still in this supercritical fluid state. So back pressure regulators are very important when it comes to supercritical fluid chromatography. Detectors. There is a wide range of detectors, as I told you, in supercritical fluid chromatography. They include UV visible detector, flame ionization detectors popularly known as FID, mass spectrometer detector, RI detectors, that is the refractive index detector, evaporating light scattering detectors, electrochemical detectors, diode array detectors, thermoconductivity detectors or thermal conductivity detectors, fluorescence detectors, electrical conductivity detectors, electron capture detectors, and IR detectors. Friends, you can see a huge horizon or a broad spectrum of detectors. This is why it has benefited more than HPLC in some aspects, because some of the detectors are not that much compatible with HPLC. So in few of the experiments today, people are preferring supercritical fluid chromatography over HPLC, but not much, because the mobile phase has to be constantly maintained in a supercritical fluid state, and it is not so easy to maintain. And even you might be aware that we have the newer versions of HPLC today called UPLC, Ultra Performance Liquid Chromatography. So friends, this is detector, the last component of our instrument, supercritical fluid chromatograph instrument. So we started with the carbon dioxide mobile phase, along with the modifier, a solvent delivering system, high pressure pumps, mixer, from mixer going ahead towards the injector, from injector to the column, from column to these detectors, including the back pressure regulators. So this together makes a complete package of supercritical fluid chromatography. Now, moving towards the advantages of supercritical fluid chromatography, it's a high-speed analysis method, low pressure drop in column issues because of the back pressure regulator constantly working, broad analysis spectrum, any type of analysis, let it be pharmaceutical, chemical, biochemistry sample, let it be steroids, let it be flavonoids, let it be food sample, let it be perfume sample, fragrance, you can do with all of them. Even analysis of thermolabile compounds is also possible. See, when you write analysis of thermolabile compound is possible, you overcome GC. Because in GC, you very well know now, sir, the compounds that get decomposed we cannot use. And the decompose resembles to the term thermolabile. But over here, when I say that you can use thermolabile compounds also for the analysis, you can very well say that yes, we have overcome the issue of GC. Again, variety of detectors. Just now you saw 12 detectors. There will be more. And the number of detectors used or compatible with supercritical fluid chromatography are much more than that compatible with HPLC. You are overcoming HPLC. Henceforth, we wrote in the very first initial slides that it's a blend of both. Benefits of GC, benefits of HPLC together forms supercritical fluid chromatography. And friends, even I have a video of Royal Society of Chemistry where the stalwarts are saying that it's an eco-friendly mobile phase. Carbon dioxide is considered to be an eco-friendly mobile phase, and hence I have written over here in one of its most important advantages that the use of eco-friendly mobile phase carbon dioxide is over here. So friends, this is what we need to know about supercritical fluid chromatography as a part of this online chromatography lecture series, or rather to say the online course. So this is all about supercritical fluid chromatography. I have discussed very basics of supercritical fluid chromatography. Thank you once again for your patience listening. Now I'm going to give you few instructions which are very important as we are on the verge of completion of our online course within the next 2 days. Friends, today is the 8th day and you have probably completed the lecture, and very soon you will be completing with the test and the feedback. Friends, right from day 1 and now up to day 8 and even tomorrow, that is day 9, I have just covered 9 topics in chromatography and not more than 20 to 25% in each chromatography. There is a lot more to do in each chromatography, but the main intention of both partners, that is Sheth M Science College Patan in the state of Gujarat and DIPAM Foundation, was to give a spark in you that there is much more to learn in chromatography. So there might be several points that we have missed here and there while discussing chromatography. Really speaking, there might be only 2% that we have missed. There might be 98% that we have purposefully missed because they can be made use study at the later stage of these online courses. And we promise that we are going to come back with many upgraded things in the near future. So, friends, thank you once again. We are really enjoying this online course since last 8 days in this mutual interactions, even through your messages, your Gmail. One more important thing before we shut down this video, I have received many of your questions and I am able to answer only 50 to 60% of your questions because I am busy maintaining this website, these lectures, this test and analysis for you. But I have promised that I'll be answering each one of them. If at all I am not able to answer the questions by the end of this day, that is 8th day, do not worry. On the 9th day morning, along with the lecture on numericals in chromatography, MCQ test, feedback, I am going to give you one more link on which you can submit all your queries. For example, I have 3 queries in this 9-day course. Then what I'll do, I will write day 1 talk so and so query, day 6 talk so and so query, day 9 talk so and so query. I will go through all these queries, compile them and take or record a lecture of an hour or two and deliberate you with all your doubts. Even then, if you have any queries, you are free to contact me for the solutions and mutual discussion. Thank you once again for your patient listening. Thank you.